Okay, first of all, I would like to thank the organizers for this opportunity to give some introductory lectures on cosmology. I already removed the term basic, and I warn you that this is going to be a crash course. The sense what will crash will be your mind. Okay? Because cosmology is a vast topic, and we don't have much time. So I tried to do basically the opposite of what I usually do. Basically, usually I prepare slides without the equations, so that people understand better. Now I prepare the slides with only me, okay? So that you will listen to me instead of reading the slides. Okay. I expect many questions, so please interrupt me at any point during the lectures. Okay, you don't have to wait until the very end to clarify your doubts. And this is a pointer not working.
Try again.
No. Yeah. Okay. So this is the plan of the lectures. The first one, I will introduce the whole Big Bang model, and then give some sketchy details about cosmological perturbations and gravitational waves, which is a hot topic nowadays. And then going on with a description of the cosmic microwave background, which is a quite important subject in cosmology for the early universe, and start to say something about inflation. The second lecture, we will finish the part of inflation. We will introduce two of the most interesting problems in modern cosmology, namely the Big Bang problem and the cosmological principle problem. There are many other problems like the dark matter problem we will not talk about. And then finally, although I was asked to prepare a course of very basic ideas of cosmology, someone yesterday asked, well, can we test the quantum gravity with cosmology? What are the observations? And I will try to give a partial answer to this question in the last part. So each part should approximately last 20-25 minutes, giving then time for questions and coffee breaks, of course. So let's begin. First of all, for the students, there are many very good textbooks in cosmology. They are different from each other depending on actually the focus you're most interested in. For instance, for cosmological perturbations, this one by Light and Little is quite good. And then there is the Library's book and others. I also put mine, not for advertising, but just because I tended to follow the same structure in of my book, and there are also a lot of exercises there with solutions, and you can check it out. Now, the whole Big Bang model, what is it? First of all, what is cosmology? How many of you did not take at least one course in cosmology? Okay, good. So this is like one really assume that we started from scratch. So if some of you gets bored, please bear with me. And I think it's important to give simple ideas to start to understand why cosmology is so important nowadays. Also in with the final objective of trying to look into fundamental physics. Okay. So why should we bother about the large scales of fundamental physics? Typically the small scales. In fact, cosmology is the study of nature at scales between 1 and about 80,000 megaparsecs. So just to give you an idea, the typical galaxy, like the Milky Way, is about the size of about 10 kiloparsecs, and clusters of galaxies have span distances about 10 to the 3 megaparsecs, and then the farthest object we can observe, the cosmic microwave background, is has the features of about 3,000 megaparsecs. This is cosmology. And the starting point maybe should be the cosmological principle, stating that from observations, the universe looks approximately homogeneous and isotropic. Homogeneous means that the same properties, you can find the same properties at the different points in space and also time, same properties in space. And isotropy means that no matter where you look into the sky, you will find similar physics and similar main properties. Okay, so this is a catalog, a reconstruction of the local distribution of galaxies up to redshift point 14. So each point is a galaxy. You see that it's not a uniform distribution, there are clusters, but if you look at larger scale, this is not a starry sky, it's another map of galaxies. Each point is a galaxy, and approximately you can see that the distribution is uniform. Of course, this is an approximation, it's not something exact. Okay, and this is yet another, actually this is a 3D rendition of distribution of galaxies, a center that this is the cosmological principle. It's based on observations. And actually, there is another object which supports the cosmological principle, which is the cosmic background. It's a background radiation of uniform temperature. Now, later we will find we will discover what the cosmic background is, where it comes from, what's its physics. But it has a uniform temperature. This is a map of the whole sky, and it doesn't have a fluctuation. So you see there are colder spots, warmer spots, but these fluctuations are very small. 1 part over 100,000. Okay. So why this number? Well, we see this. This is one of the open questions of the standard Hawking model, which was eventually solved by intuition. Now, a mathematical way to state the cosmological principle is to use a specific metric and a specific theory of gravitation. So let us assume from now on general relativity, so no modified gravity, no quantum gravity, and let's see how far we can go with general relativity. Okay. So this is the background of embodying the cosmological principle, which is called Freeman-Lemaitre-Robertson work, FLRW for friends. And it is characterized by this scale factor, which is a function purely of time. So this is stating that the universe is homogeneous because of this metric component that does not depend on the spatial points. And then the spatial part of the metric may or may not depend on the curvature. So the universe, in principle, can have a zero curvature being reflected, or constant positive curvature, or constant negative curvature. So in these cases, k would be respectively equal to 0, -1, and +1. And another variable one can use, actually it's used quite often, is called conformal time, which is defined here. And with this coordinate transformation, you can rewrite the line element as being conformally equivalent to, well, it's Minkowski when k is equal to 0. Okay? So you can factorize with a scale factor like this. And the scale factor relates two types of distances. There is the physical distance, or also called the proper distance. And then there is the moving distance, which is the physical distance divided by k. And this is the distance observed by a moving observer. We will see what this means later. Then let's have more concepts if these were not enough for you. One is redshift, which is the inverse of a scale factor, where A naught is the scale factor today. But since this is a mathematical quantity, we can set A naught equal to 1, and so redshift is just the 1 over A. So Z equal to 0 is basically it describes indicates the distance from us. So Z equal to 0 corresponds to today, and larger redshift corresponds to farther scales or even older times. Then the time derivative of scale factor divided by A is called the Hubble parameter, and the inverse of the Hubble parameter is called the Hubble radius, or Hubble distance, or improperly Hubble horizon. Basically, it's very easy to see that this distance, this gives the proper distance of the proper size of a patch, a causal patch of the universe centered around us, meaning that it's a set of all points which came into causal contact, okay, from the beginning. It's not actually this definition is that of a particle horizon, but the Hubble horizon is approximately equal to the particle horizon during the first stages of evolution of the universe. So it's easier for these lectures just to talk about the Hubble distance instead of the particle distance. Now, one can measure the Hubble parameter. This is its value today. It's parameterized by this dimensionless parameter h, which according to modern estimates is about the 0.68. Probably this figure is not updated because this is Planck 15, but the Planck legacy value is not far from this one. We will fix all of these mini details in the lecture notes, so don't worry too much about the exact numbers. The inverse of a Hubble parameter gives a rough estimate of the age of the universe. So taking the inverse, you get 14.5 billion years, which is not quite far from a better estimate, which can be found by considering more in detail the content of the universe. And if you do that, you get a number which is about 13.8 billion years. Okay, so this is an estimate of the age of the universe. So what happened then at t equal to 0? We will see that. This is just pure GR. I just recall that this is the Einstein reduction, where the each scalar is defined as usual through the Leibniz connection. And I like the signature minus plus plus plus, but of course you can work also in the mostly minus signature. And as an exercise before going to bed, you can calculate the variation of a each scalar and of the determinant of a metric, and from that you get the Einstein equations, where we also introduced the cosmological constant term, where G mu nu is the Einstein tensor, G mu nu is the energy momentum tensor, which we'll have to specify. For instance, if we assume that the matter is given by perfect fluid, then we can define a pressure and P, capital P, and energy density rho, where U is the velocity along the word line, and in a specific example of perfect fluid, we see many perfect fluid, but in a specific example actually is a scalar field, and a scalar field with a potential V, and the equation of motion of a scalar field on a generic background is box field minus first derivative of a field of the potential equal to 0, where the box is the Laplace spectrum operator, which for a scalar is particularly simple because it's a second order derivative, but decorated with metric determinant terms. Okay. On an FRW background, this equation of motion turns into this, where fields are perfectly homogeneous. So remember that things according to the cosmological principle do not depend on the spatial points. And there is a friction term here. So D is the dimension, topological dimension of space-time. Since we live in 4 dimensions, let's put the D equal to 4. So here you have a friction term. So in general, if you want to do field theory on an FRW background, you will have to solve the harmonic oscillator with the friction. The equations, the Einstein equations, reduce in purely homogeneous and isotropic setting to the so-called Friedmann equations. I just sketch here the only non-vanishing values of the Levi-Chivy connection, but you can calculate your curvature tensors and eventually calculate the 0-0 component of the Einstein equations and eventually the trace. And these are the 2 equations that come out. The first Friedmann equation tells you that the square-Hubble parameter is proportional to the energy density of the universe, total energy density of the universe, and now you have 2 more terms. One is the cosmological constant term, where lambda is constant, and the other is a term which comes purely from GR. It's not something that you could derive. You could derive these equations from Newtonian mechanics, but you wouldn't get the curvature term. And this is the second Friedmann equation, telling you that the acceleration of the universe, A double dot, is proportional to minus rho plus 3p, plus eventually lambda. An exact solution of the Friedmann equation is the power law expansion, where the scale factor is just the power, is the power law, and the Hubble parameter goes as 1 over t. Where P is related to the equation of state of your fluid, where for a barotropic fluid, the relation between pressure and energy density is given by a constant down. Now notice that when t goes to 0, the scale factor goes to 0, which means that your metric becomes degenerate. But not only that, the Hubble parameter goes to infinity, which means that also the energy density will go to infinity. So you have zeros and infinities, and this is a problem, which is a big problem, which we will see in the second lecture. Okay. You may ask, are there solutions like this? Do they always have a bagger? I will leave this question unanswered until the second lecture. Okay. So if you cannot really sleep tonight, please ask this question again at the end of the lecture. Okay? Now, what's the concept of the universe? There is well, we can make a catalog depending, classify the content depending on the question of state. We have radiation because we have photons, we have neutrinos, and that corresponds to a component with W equal to 1/3. And the radiation energy density in this case as the cube, the 4th power of 1 plus z, where z is potential. Then we have dust, which in cosmology is often called matter. So I feel the theoretician would call everything matter. In cosmology, sometimes people call matter only dust. So let me call it dust to make everybody happy, which corresponds to a pressureless fluid whose energy density scales as the cube of 1 plus z. So they grow when you go backwards in time, when z grows, and at some point they were equal to each other. Nowadays, matter corresponds to about 1/4 of what we observe, and the radiation is a very, very small fraction that you don't even see in this pie chart. There was a point in the past where the contribution of matter radiation was about the same, and this epoch is called the matter radiation epoch, which happened when the Z was about 3,000. And then we have another component, which is actually the largest, which occupies about 2/3. It contributes to about 2/3 of the content of the universe, which we call the dark energy. Why? Because we don't know what it is, but why we call it dark? Not because it doesn't interact with light. Yes, that's true, but mainly darker because we don't know what it is. And if you take the second Friedmann equation and you plug a barotropic fluid, you will see that well, basic observations tell you that the right-hand side is positive, so the left-hand side must be positive, meaning that we are accelerating. And this will constitute the cosmological problem, which we will talk about in a second lecture. In fact, to describe acceleration, it's very useful to introduce the so-called first Rover parameter, which is minus h dot divided by h squared. And you have acceleration as soon as epsilon is greater than 1. Sorry, smaller than 1. So the acceleration when epsilon is greater than 1, and the acceleration when epsilon is smaller than 1. When epsilon is negative, you have a super acceleration. Now, observations tell us that the equation of state of dark energy resembles that of the cosmological constant, because the W, the barotropic index of dark energy, is closer to -1. We are not really sure if it's very, very close to -1 or exactly equal to -1, but it's something that well, observations will refine this interval. But so far, the value -1 is within an experimental error. So we cannot exclude that the dark energy is given by a pure cosmological constant. Okay. We will use this parameter after also for the early universe, so it's a very, very important. Now, this is a timeline of the universe up to some time in the past, not really to t equal to 0, because we're not ready for that. But you can see, actually, we can associate the temperature to any epoch of the universe, and the temperature is proportional to the redshift. Why? Well, I just the intuitive reason is that if you take the Boltzmann law for radiation, energy density, that energy density goes as the fourth power of a temperature, and since we saw that this also goes at the fourth power of 1 plus c, then the temperature is proportional to 1 plus c. Then you have some prefactors that depend on the number of species in the universe, but this number is not important. I want you just to appreciate that when we go backwards in time, then the temperature increases, and here in the table I reached the LHC energy, leaving what happens after what happened before for the partial inflation. Okay, but this is why it's the hot equilibrium model, because the universe was quite hot for most of its life. For instance, when it was 380,000 years old, which is the age of the cosmic macro in the ground, the temperature of the universe was still about 3,000 Kelvin. And nowadays, it's cold because it's 3 Kelvin only, which is the temperature we saw at 2.76, which we saw below the macro. And in between, what happened? Well, we will not have time to discuss this. Let me just sketch briefly. At first, the matter and I mean, were no atomic structures, so particles were scattering among each other individually, and atomic nuclei started to form only after 2 seconds since the beginning, and a few seconds afterwards, atoms formed, and so then photosynthesis began, and it lasted for about 20 minutes. After 20 minutes, already the universe, there were atomic structures in the matter was organized in atoms in the universe. This epoch is called the Big Bang electrosynthesis. It's very important because it gives very tight constraints on a number of parameters. So it's an important reference when you want to do cosmology. Radiation matter equality, that's what I was talking about before. And the age of the universe at that time was about 70,000 years. And its causal size was about 39 kiloparsecs. So it was about 4 times the size of a galaxy. So this is not the size of the universe. The universe could be infinite as far as we know. Okay. But so the only thing we can make statements about is about our causal patch. So the size of a causal patch at that time was only, in quotation marks, 40 kiloparsecs. And the first stars formed when the universe was 100 billion years old, and the causal patch was about 110 megaparsecs, which is already the size of a cluster of galaxies. Okay. Questions?
The universe can be infinite today. This means that it was infinite all the way around to the way back.
Exactly. Yeah. Yes. In the origin, so it formed at all points at the same time, and then yeah, we can talk about that with a different problem. But yes, if it's infinite, it was like that since the beginning, because the curvature is constant.
Another thing, I will be speaking about time here in 20 seconds or 20 minutes.
Yes.
This is for a certain observer. It will be for an observer which is addressed with respect to the macro background.
Here we are assuming the cosmological principle, meaning that all observers, the clocks of all observers are synchronized. So an observer in the galaxy of Andromeda will basically compile the same history of the universe as us.
But he's not moving. It is not a movement observer with respect to observers which are moving relatively each other in a certain different the intervals of time.
Yeah, that's true, but it depends actually on what phenomena you are observing. So for phenomena of cosmological size, then the cosmological principle is the approximation, and that implies forcefully that all observers can identify the same clock. More questions? No, these are the actual values. So it's just extrapolating with well, you know that about between 2/3 and 3/4 of the dark energy And you know that one quarter is made of matter, dark matter, for that matter, and sorry from it all. And you plug this information in your Riemann equations, integrate your Riemann equations, and from that you get the profile of the Hubble parameter. The inverse of the Hubble parameter will give you basically this radius as the inverse. This is actually the practical process, not really one radius. Okay? I haven't included the practical process, but it's similar to the Hubble. Anyway, it's clear from this picture, even if we haven't gone up down to t equal to 0, but the universe, if we go backwards in time, the universe will be hotter and hotter, and that's why it's called the Hubble. Okay, the cosmological principle is useful, but up to some point, because we know that the universe is not homogeneous, and is not isotropic either exactly, because if it were like that, we wouldn't exist in this room. But anyway, at the cosmological scale, fluctuations around this FW background are very small. That's why one talks about cosmological perturbations. The idea is to go to full GR and expand around the background metric, which you can take as an FW metric, or the sitter, which we will talk about later, and then add a small perturbation. This small perturbation H mono can be divided into three sectors: scalar perturbations, tensor perturbations, and vector perturbations, depending on how you decompose your metric, your full metric. And one can describe these three sectors separately. Okay. The vector sector is not very important because vector perturbations are strongly damped, so they don't play in, at least in GR, they don't, and in very James we will talk about, they will not play any. And let's begin with tensor perturbations, which are actually easier, much easier than scalar perturbations. Tensor perturbations are embodied by this metric with spatial indices alpha beta. And here we're working in conformal time. So remember that when the curvature is 0, so let's assume a flat universe of simplicity, the line element is conformally equivalent to Minkowski. So here we have basically perturbing Minkowski, but instead of proper time, we have conformal time. And we can always set this because in diffeomorphic invariant theory, in any dimension, you can choose a transverse traceless gauge, where the trace of H mono is 0, and the first derivative is also 0, and you don't have mixed components. So this is fully general. We are just making use of the symmetries of the theory, and we decompose this H alpha beta into two polarization components, where H plus and H cross are scalars, which depend on space and time. So X equals all the coordinates, and then there are two polarization matrices. It's an exercise which I recommend you to do at least once or twice in your life, to get the equations of motion for the tensor perturbation, and you will find that thanks to this gauge choice, the variation of the Ricci tensor is quite simple, because it's proportional to the box of the H-mono box is actually the terminal class of operator of the background metric. So it will include also the friction term. Remember, we are working on FW. And the variation of the Ricci scalar is zero. So eventually, this is the effective, this is the action quadratic order in the perturbation, and you see that basically you have two scalar modes with a canonical kinetic plus a massive node if you have this is not important. Now, just by making a change of notation, let's call this each polarization mode as a phi, and this is the equation of motion. Remember, this is in actual conformal time, and the h calligraphic h is the Helmholtz parameter in conformal time. So it's where prime is d tau. Remember that d tau was dt over a. So you have a friction term. And you have an effective mass term, which now depends on time because C, this is actually a generic scale of the mass, but from the graph, of course, m is equal to 0. By making a theory definition where you multiply phi with alpha with a, with scale factor, this alpha is equal to 1 in 4 dimensions. So let's assume that the alpha is equal to 1. You get what is called a Mukhanov-Sasaki equation for the perturbation W. And you can see that there is a kinetic term, where now I went to momentum space. This is co-moving momentum. And the capital M is a time-independent object, where even when the mass is 0, it doesn't depend on conformal time as 1 over tau squared. Okay? In 4 dimensions, m squared is 2 over tau squared. So it's a harmonic oscillator, but with a time-dependent mass. And solve it exactly. And this is quite good. Let me just show you the asymptotic solutions, which are easier to understand. So when the momentum part is much bigger than the mass part, then this equation reduces to a standard harmonic oscillator, whose solutions are plane waves. Okay, so the perturbation has is a superposition of plane waves with a given amplitude. However, the things change when the common momentum is much smaller than the mass term, and in that case, you can basically you find that the easiest solution is a constant. Okay. Of course, you have to match these two asymptotic solutions at some point. But nowadays you don't even need that because you can solve the Mukhanov-Sasaki equation exactly. But this is just to give you an idea of these two regimes. And notice that it's easy to show that tau is nothing but the co-moving Hubble radius. Oops.
Just to be sure. Push the button here. Blue one. You selected it now down.
No, but it's not up.
This is the one here.
Okay. Okay, sorry for interrupting. Since the tau, actually the absolute value of tau is given by the moving Hubble radius, approximately. See Hubble radius divided by A, so it's called Hubble radius. These two regimes tell you how cosmological perturbations behave inside and outside the horizon. So inside the horizon, perturbations are superposition of plane waves, but outside the horizon they freeze. So since the moving Hubble radius changes during the evolution of the universe, when a perturbation of a certain wavelength goes inside or outside the horizon, it will freeze or start to oscillate. This is fundamental to understand primordial perturbation. Scalar perturbations follow the same logic. You expand the metric with now with the scalar quantities, actually 4. 2 of them can be gauge fixed to 0, B and E, and you end up with only two scalars, one in front of tau, this is what we would call the gravitational potential, and another attached to the spatial particle metric. These perturbations are generated by fluctuations of the matter content of the universe. So you also have a perturbation for energy density pressure. I will not write down the equations of motion here, but eventually you end up, if you combine these perturbations into this gauge invariant quantity, which is called zeta, the curvature perturbation on the uniform density hypersurfaces. There is no shortcut for this name, sorry. So you can memorize it once and then just call it zeta. This quantity is gauge invariant, and by combining it with some prefactor, depending on the background, you can end up with a Mokano-Sasaki equation of exactly the same type, but with m squared, a bit more complicated. But you do get the same equation. You do get the same equation, but W has a different definition, and m squared has a different form. Still with a 1/tau squared. I don't prove it here. I just it's not okay. Now here we're talking about cosmological perturbations. Okay, but there are other types of perturbations, for instance, gravitational waves of astrophysical objects, which, as you know, have been discovered in 2015, but we knew it a bit later, of a LIGO-LIGO collaboration. And this is the waveform of that black hole binary source. So this is, if you want, how a time-dependent H-Munu coming from an astrophysical system would look like. So how do you cannot use the previous formalism, because that is valid on a homogeneous background at very large scales. Here we're talking about gravitational waves of higher frequency. So you have to do things differently. And this is a start, but it's not the end. This is a very difficult subject. I am still learning myself. I'm not an expert in gravitational waves, but I'm learning little by little. Once again, you perturb your Einstein equations, and you get you start with a tensor perturbation like before. But now you have matter, so you take into account the energy momentum tensor also when you are considering tensor perturbations, and you end up with this equation where S Munu is just a combination of the energy momentum tensor and its trace. You can solve it, and it's just a convolution of this matter source with the retarded green function solving the problem. And actually notice this eta means that now, so far, I am considering a cosmic background. So basically a gravitational wave in what is called a local wave zone. meaning a zone which is much bigger than the characteristic wavelength of a perturbation. So it's quite far away from the astrophysical object. You can imagine two spinning black holes, for instance. But it's much shorter than cosmological distances. So I don't need to take care of the cosmological expansion. So in the local wave zone, it turns out that in 4 dimensions, the gravitational wave is proportional to 1/r, so the distance from the source, times a function which depends. It depends also on time. Now, if you want to go to cosmological distances, then you have to include also the cosmic expansion. And an interesting observable to consider is the luminosity distance. What is the luminosity distance? So for a source of photons, so let's put aside for a moment gravitational waves and just consider a source of light. The luminosity distance is defined by this formula, where F is the flux, the mechanical flux of light, and L is the power. And one can show just by some redshift hocus pocus that you can find actually in. I found it only in one book, well, 2 books. One by Major, Gravitational Waves, and the other by Cosa and Luchina, the last edition of Cosa and Luchina. Anyway, you find that the luminosity distance for a source of light is given by the moving distance divided by the scale factor. So if you write down the expression of the moving distance, which you obtain by integrating from a certain redshift z, which is the redshift of the source until today, you end up with an expression this type. And when the Hubble parameter is approximately constant, then the luminosity distance is inversely proportional to the Hubble constant, and directly proportional to the redshift. So this approximation will be valid at the small redshift, much smaller than 1. Otherwise, this is the general form. So if we plug to extend this formula to cosmological scales, we have to attach scale factors, and the correct way to do it eventually leads to a guess, to a result which can be also guessed, maybe that you replace the moving distance with the luminosity distance. So a source of gravitational waves and the photons is called the standard siren. We have this relation, namely that the amplitude will be given by the inverse of the luminosity distance of the object, as measured from its optical counterpart. Okay, so standard siren is something that emits both gravitational waves and photons. We know one, which is the event GW17-0817, and in that case, its luminosity, this is a binary neutron star. Its luminosity distance in that case was about 40 megaparsecs. I'm not updated about the most recent catalog of LIGO Bibliocara, but now we are counting many gravitational wave sources. And among them, we expected to find from time to time standard sirens. For instance, in the experiment LISA, you know LISA? Who doesn't know about LISA? Okay, LISA is an interferometer which will be made of the 3 satellites launched into space, so it will be the largest experiment in human history, largest in size. And it will be launched about, well, hopefully, 10-15 years from now, and it is estimated to observe about between 60 and 80 standard satellites. So we're not talking about hundreds of standards, but still a few doses. So if you take a different theory from PR, then maybe you can find that the amplitude is not proportional to 1 over the luminosity distance of the optical source, and we talk about this behind Gauss. There is another sector of gravitational waves which is very, very interesting. It's called the stochastic gravitational wave background, which is basically a superposition. So here we are talking about a gravitational wave coming from coming to us from an individual object, not a physical object. But if you have many sources of gravitational waves, gravitational waves interfere with one another, and then we create a background which is called the stochastic gravitational background, and depending on what is originating gravitational waves, this stochastic gravitational wave background will have different properties. So the energy density of this background is defined by basically the kinetic term of the tensor perturbation, and the gravitational wave background itself, the stochastic, sorry, the GW background itself is defined by this formula. So the logarithmic variation of the energy density with respect to the moving wave number divided by the critical density. Critical density, by the way, is it's just a number, but you can get it from the Friedman equations. If given by basically the Newton constant and the Hubble constant. So if you have a primordial source of gravitational waves, these gravitational waves will form a spectrum, which I call PT, and this spectrum will evolve in time. So because of this gravitational waves coming from afar, we go through different stages of a universe where radiation was dominating, when matter was dominating, and when dark energy was dominating. And so eventually we will have to correct this primordial spectrum with some what's called the transfer function. And what we will observe today is called the stochastic gravitational wave background of from some primordial source. Primordial means very early. So this is a plot of the stochastic gravitational wave background as a function of the frequency. And these are the sensitivity curves of some experiments. This dark gray is the bound given by LIGO-Bingo-Cagra. So we haven't observed any stochastic background so far. So we know that at the frequencies of LIGO-Bingo-Cagra there is no background. LISA will probe lower amplitudes at the different frequencies. And then there are other experiments like Einstein telescope, which now the European Union is strongly supporting, and the Japanese design. So there are other bounds coming from the dynamic synthesis and the cosmic microwave background. And the typical stochastic background generated by inflation, which I expect that those of you don't know cosmology, don't know what inflation is. It's an early phase, which we'll see soon, which has the capacity of producing a scalar and tensor perturbations. So tensor perturbations generate a primordial spectrum, which we observe in the CMB, but it also generates a stochastic background, which we can, in fact, we do not observe today because it's very, very it has a very, very low amplitude. It's here. It's this black curve, which is far below all the experiments proposed also for the next generation. Okay. So I think it's a good time to stop, because maybe you wanted to take a break. Do you have questions about this second part? Yes.
So I have a question about this gravitational placing of communication. So what period of inflation are we talking about? Is it like preheating or something?
Yeah. Maybe we can talk about it after I talk about inflation. But I mean, reheating will affect the stochastic background at higher frequencies. It actually will bend it down. But maybe it's better to, if you ask me this question again after I introduce inflation, so that everybody knows about it.
You have mentioned that inflation will produce signals in the TMB that will be seen, and also in this gravitational wave, there is a stochastic phenomenon. So there will be related on this in order to follow from reflection.
Yeah, I mean, this power spectrum is the same. So, and that one is constrained by at the frequencies of CVPs. So this is basically the upper bound of the amplitude of the tensor spectrum, above which you already migrate observation. But then the same function here enters into the stochastic background and produces this curve. This is an example taken by star visiting, which is the sweet spot of the most favored form. I don't think that it by people model of inflation, and that will produce this curve, which basically is an extension of the Brahmana spectrum, but which underwent all the recent cases of relation domination, matter domination, etc. With the transfer function. And of course, depending on the specific models of inflation, we will get a specific stochastic background. So for different models of inflation, we will get something. No, because here we are assuming some standard model of inflation. But in the last part of my talk, I will introduce some models where after this curve goes up, and it can intercept the cycle, and probably none of the other experiment. You need a very different physics to get higher frequencies. But then you also have to take care that you have this PBN bound, which goes to all frequencies, and then you have to. You cannot have a spectrum which goes all the way up because from one that is exclusionary. So you have to take into account actually
How easy is it to distinguish between this signal and that signal from the electric phase transition, for example?
I think yeah, that's a good question. Different models of high energy physics or modified gravity or quantum gravity give very specific shapes of the background, of the stochastic background, and in principle, one is trying to get something which is not fine-tuned, so where the parameters of my model are reasonable. So I think I'm not an expert in phase transitions, but in LISA, for instance, there are people who work on models of phase transition precisely to get some reasonable model that could intercept the sensitivity curve. And I can tell you that in general, models of quantum gravity, as far as I know, cannot reach really the Lisa curve. So if you observe the something, it could be that it has a different explanation than the quantum gravity class. Be phase transition, as you say, or something. But the subject is quite open, and we also have to define what quantum gravity is in this case, because there are many approximations, and I would say that there are so few models giving reasonable stochastic backgrounds, which we are not yet talking about the degeneracy problem. It's more a problem of really finding something. We are at the stage of let's find something. Something good. Good means with reasonable theoretical assumptions and moving. Questions? Yes. Yeah. In fact, the main focus of science of these experiments is on astrophysical sources. It's not on Riemann background. Here I'm talking about Riemann background, but of course, here the lion's share is given by stochastic background astrophysical sources like supermassive black holes. Here, you would have something much more interesting for this experiment. Or you want to continue? start. So, before I wanted to make an announcement about the tutorial, since I see no point in proposing exercises of GR for cosmology, which you can do by yourself at home, I think it's better to dedicate my time to question time. So after this talk, if you ask a question and you weren't happy about the answer, or if some new question comes to your mind, just send me an email here, and I will try to collect all the questions I get. Let's say that the line is tomorrow at midnight, so you have a couple of days to think about questions. Then in the tutorial on Thursday, I will try to compile the questions and give an answer, and we can have a debate together. Or if could be also questions about the things that you haven't seen in this talk. So we dedicate the tutorial time to this collective exercise. And of course, also during the tutorial, if you have new questions, if you didn't send by email, you can of course ask. Okay, I'll try my best to give an answer. Is that clear? Yes? No? I don't know. Okay, good. Now, cosmic microwave background, CMB for friends. You have seen it already in the first part. It was discovered in the T65, thankfully because there are actually different regions of other aliens which are nested inside this antenna, and the two technicians which were in charge of the instrument went to check because they were detecting some strange background. But after removing the nest, they kept hearing this buzz, and eventually that was the first detection of the cosmic microwave background, which led to further investigation. Remember when I was an undergraduate student, results from the COVID mission were still fresh, and so about 30 years ago, this was a picture of a cosmic microwave background. So left-hand side of this map coming from the Milky Way, so the dark regions of the Milky Way plane, which are opaque to the background. We started to see some anisotropies, which WMAP, American mission WMAP, further defined, and we ended up with now with a map of the plaque, which we saw in the previous slide. It will be too painful to go back, so sorry. Just remind it in your memory. And probably that's going to be the best that we can observe. Okay, plaque really reached the top sensitivity as far as temperature map is concerned. So any further progress will not deviate much from what we already saw. Okay. Anyway, what's the cosmic microwave background? So we saw in the first in the table of the timeline of not so early universe But when the universe was about 1 second old, it was made with a hot plasma of matter and radiation in thermal equilibrium. After a few minutes, the nucleosynthesis of light elements began, like deuterium, helium, lithium, and which ended when the universe was about 20 minutes old. As the universe expanded, then this plasma started to cool down, and protons started to capture electrons, giving rise to atomic structures, process called recombination, and eventually matter and radiation decoupled. What happened because the scattering? So this plasma was opaque, so photons couldn't travel freely because they were scattered endlessly by the rest of the components. But as the density lowered, then the entry path of photons increased, and at some point they were able to move freely, and the universe became transparent to light. So this is automatic correction of PowerPoint. I'm sorry, I thought I spotted all that. So as the density of diffusion centers decreased, the universe became transparent to light. And the cosmic microwave background is a photograph of that moment. So it's like observing the clouds in the sky. You cannot see past the clouds. That's the farthest point you can see the sky. The CMB is something. It's a picture of the universe when it was about 300,000 years old. You cannot see beyond, because beyond light was not free to travel. You can see beyond with other sources, like radiation waves. Radiation waves, the CMB is a transparent radiation wave, so we can get much older signals carried by radiation waves. But that's another story.
Between the moment where explanation starts and the moment where the universe becomes transparent.
No, I mean we are talking about some specific epochs of a specific redshift, but in fact we are talking about smooth evolution. So consider this as just a crude approximation of what really happened, because it's more.
The time of the combination starts, then you need some time for the density of the diffractions and the universe.
Yeah.
But it's a short time.
Yes. Compared to previous evolution, it's a short. It's around 0. So how do we describe the cosmic microwave background? How do we create these maps? So we have a sphere, which is the sphere of observation, and then we want to create a map, planar map from this sphere. At each sphere, at each point in the sphere, we can measure the temperature. How do we do that? You do it through spherical harmonics. So you decompose your temperature fluctuation delta T over T naught, where T naught is 2.76. In terms of spherical harmonics, which are given by Legendre polynomials here, this expression is not, the details are not important here. It's just I wanted to show you how you can progress. And you call A and M the coefficients of this expansion. Now we make an assumption, which actually is good approximation of what we observe, and it has a motivation in inflation. So without inflation, there are several problems in developing data, which I haven't mentioned. And one of them could be, well, why is this assumption correct? So keep that in mind. The assumption is that the temperature anisotropies come from a causal process with an isotropic Gaussian distribution. What does it mean? It means that the real and imaginary part of these coefficients are independent, and up to some numerical, unimportant numerical factors, they follow a Gaussian distribution, where the spread is the temperature under the spectrum, which is denoted as a CL. Now, with this assumption, you can consider this object, which is a sum over the M index, and take the average over all possible skies. So you can imagine that you have a spaceship, and you take a full map of the CMB on Earth. Then you go on another part of the universe, and you take another set of observations, so another map of the CMB, and so on and so forth. And you take the average of what you saw, and this is the temperature under a spectrum. You cannot do that, then in fact this creates a small problem. Anyway, it turns out that the temperature under a spectrum is related to the chronological spectrum by this integration over the common momentum, where J is a spherical Bessel function. And in this part of the topic, we see many formulas without a derivation. That's because this subject is quite complex, and we don't have time to derive all the formulae. Here, the important thing is to notice that you have a map, you have data of a temperature. You can translate them as a spectrum on multiples, is L called multiples, L. And in turn, this multiple spectrum is related to the chronological spectrum in terms of the moving number K. So, but we cannot observe, we have only one map, okay? One sky. We cannot average over all possible skies. So, one can assume, and this is called the ergodic hypothesis, that conveniently the average over an ensemble of all possible skies are equivalent to spatial averages over one sky. Okay, that would be very good, because we could replace those expectation values, those averages over just taking spatial averages over the sky, which means that, for instance, the spectrum is the 2-point correlation factor. So I basically have to take 2 points of the sky and correlate, measure the correlations based on all the points I can. However, so this would mean basically integrating over the spheres too. But this ergodic hypothesis does not work. Why? Because this is true only for spectra over a continuum. But the angular spectrum is over a discrete set of values, because these multiples run from 0 to infinity. Okay, it's here. Okay, so this hypothesis doesn't work. However, you can still apply it, because we cannot travel in a space yet. And if applied, you have to take into account some error, which is called the cosmic variance. And the cosmic variance is can be calculated, and it's given by the square of the multiple spectrum divided by 2L plus 1. Which means that the higher L, the lower the cosmic variance. So this is the multiple spectrum, but it's actually normalized in a different way. But yeah, if I remember correctly, it's this. It doesn't really matter now, okay? But I just show it for completeness. So this is what we observe. These points are the multiple spectrum of a CMB, and the red curve is the Laplace CDM model. Okay, so this is the theory fitting the data. These are the multiples. Smaller multiples mean larger distances. So smaller, moving with number, also larger distances. While high multiples correspond to small distances. It means that this spectrum, for instance, at L of order 1000, is taken not by correlating one point there and one at the opposite part of the sky, because it would be large distance, but at a very small angular resolution. Okay? While here are the largest possible distances. So we are correlating distant points. And this blue band is a cosmic variance. So it's bigger here at the low multiples, and it becomes negligible. You cannot really see it here already when L is of order of 100. Okay? So it means that any model you want to test with the CMB data, any model deviating from GR, which produces a deviation at the low multiples, well, should give a signal higher than the cosmic variance. Unfortunately, in the literature, you find a lot of models which say, I find a deviation of a spectrum like a suppression of low multiples. Then you compare the fact with cosmic variance, and you see that it falls within the value. So you cannot really talk about an observable deviation from GR. Okay. And unfortunately, high energy models or modified gravity models, unfortunately, this is life. If they predict some changes, they are always on this screen. Because larger scales correspond to well, we see that in the meditation. Basically, larger scales are also more ancient, and they underwent more extreme regimes with possible deviation from GR. Okay, so this is cosmic variance. Keep it in mind when I want to do model building and testing it with the CMB data. So this is a sketch from a paper by Corfu2021, but I like it. That's why there are here coffee maps and not the plant maps. This is a rough sketch of how you get physics from a CMB. Your instrument gives a data set, time order the data, and at the different frequencies. So you can organize this in frequency bands, and so you will have a map for each frequency band, and eventually by some black box, which I since I made the edition, I think about you really what it is, but eventually you extract one of these beautiful maps that we shamelessly shamelessly shown in our talks. And from the maps, we have the mathematical decomposition we've seen. We get the power spectrum. And from the power spectrum, so from the amplitude at, for instance, no multiples, the position of the peaks, the amplitude of the peaks, the number of the peaks, and some other features, one can extract an estimate of the parameters of the underlying. So here we're talking about, for instance, for WMAP, if I'm not mistaken, we're talking about 10 to the 5, order 10 to the 5 bands, and each map has about 10 to the 7 pixels. So it's a lot of information. But eventually, here you estimate an order 10 parameter. Okay. So at this point, you must have a model which you want to test. And here, so the reference is the lambda CDM model, which is composed of cold dark matter, the CDM, and a cosmological node. Remember that the universe is accelerating, so we have to take into account something which makes the universe accelerate. Okay, so what are the features of the CMB spectrum? There are many, which I will not talk about, like for instance the damping theta. There is a lot of physics involved here, and it will take a whole series of lectures by itself. So here I will try to sketch, hoping that this sketch is understandable. So I concentrate on two features, this plateau and these oscillatory peaks. So a plateau comes from the so-called Saxe-Wolf effect. It turns out that for at these low multiples, the scalar perturbations can give an explanation of this plateau, because this theta is a delta t over t. But you will remember, okay, theta is basically the temperature fluctuation. And at low multiples, it's proportional to the gravitational potential, which was a 0, component of a perturbable metric. And the Saxe-Wolf effect is well, this observation that this gravitational potential is constant at low multiples. By low, I mean smaller than 100. Well, there is an explanation in quotation marks, which is the following. Remember that the multiple power spectrum, multiple semi-spectrum, was given by this formula, so integration of the Fermat spectrum times some spherical Bessel function. And you can parameterize the Fermat spectrum as power law with a constant amplitude A and some power n of the moving wave number. Okay, so and this tau naught, so which is the moving horizon today, is introduced just for to make this quantity dimensionless. Now it happens that if you plug this here, you can integrate it exactly, and if this power n is 0, called the Harrison-Sandowich spectrum, then CL is a constant. Of course, this is not an explanation, because it's just shifting a question to another question. The question is, why should I consider a primordial, almost a constant primordial power spectrum? Almost, because this is not observations that tell that this n is not identically 0. So the question is even worse. I mean, why do I have to fine tune a parameter closer to 0? However, this is just one step further to the actual explanation of this. But here we are talking about semi-physics. So we're not talking about its explanation from the perspective of fundamental cosmology. Okay. Anyway, we have this observation that at low multiples, the spectrum is flat. Then the other characteristic feature, which you could appreciate in the plot, are these acoustic peaks. And I just tell in one line where they come from. They come from the fact that photons coming from a CMB have to go through potential wells given by the baryonic method distribution. And the getting in and out of these potential wells can be described by harmonic oscillation. Remember that scalar and tensor perturbations obeyed a harmonic oscillator problem with friction, or harmonic oscillator with a time dependent mass. And when you study the physics of acoustic peaks, you use the type of equations, and you eventually find that at high multiples, you have the predominance of this effect that is given by called acoustic oscillation. And then you have the damping tail and the other features which are not here, but there are also other types of Saxon effects. And by the way, notice that the main contribution of this spectrum is given by scalar perturbations. The tensor perturbations, in general, are from a theory, are smaller. Okay, we will also see why. Now, so I have an underlying model, lambda CDF. They don't like lambda CDF because I think that Einstein was wrong. You find in the graph event. You take another model, and you want to test it against the data. But if you change parameters, or change the values of the parameters, you will alter your theoretical prediction. For instance, if the universe were open instead of flat, we would observe a spectrum with a higher amplitude and also a displacement of the position of the peaks. I mean, we have several peaks, so for each we have a position along the multiple line and an amplitude. So by changing the parameters, you will affect both the position and the amplitude. So if you change the curvature of a universe, you will find a different spectrum. And that's why we say that the universe, the observations tell us that the universe is flat. Because the spectrum we observe is compatible with the curvature k equal to 0. If the universe were closed or open, we would observe a different pattern of cold and hot spots. We could see bigger spots, bigger colder and bigger dark and bigger hotter spots, or vice versa. Also, if you change the value of the cosmological constant, you get a huge shift in the amplitude, and eventually also the position of some rings. And the value of lambda will constitute some interesting point we discuss the next time or at the end of this lecture. Another parameter you could play with is the variant density. You change the variant density again, you have a change in the features of your CMB spectrum. This is how you can extract estimates for your cosmological parameter. Of course, we need a background model. You cannot do it in a model dependent way. But at least this is a model dependent way. Okay? Yeah, let me talk about this slide and then maybe I collect some questions. We said that this spectrum is basically given by the scalar part, but we also have the tensor part. We also said that the vector part doesn't play any important role in this discussion. So it is customary to describe the scalar and tensor spectra with some parameters. The scalar spectrum itself is the power spectrum of the geometry perturbation on uniform density hypersurfaces, theta. And one can define the scalar spectral index as the logarithmic variation of the spectrum with the convolution. And here it's only a convention that it's called ns-1 instead of ns. It's just a convention. So a constant power spectrum will correspond to ns equal to 1 of the Harrison-Zeldovich spectrum. If this spectrum were a pure power law, then this would be the only parameter you need except the amplitude. But in general, you don't know a priori that your spectrum is a pure power law. So you have to introduce other parameters, for instance, the variation of a scalar index with respect to the scale, the moving wave number, which is denoted as alpha s. And it's called the running of a spectrum, because it's running of a moving scale. For tensor spectrum, you do the same. The tensor spectrum is given by the contribution of the two polarization modes. You remember that gravitons, in the classical acceleration waves, have the two polarization modes in 4 dimensions. So the total spectrum is given by the sum of the spectrum of each mode. And again, you define a tensor spectral index, which now is nt with -1. So a constant spectrum will correspond to t equal to 0. And then you also define a running, but in general, the running does not play a role for variable universe. It doesn't play a role for gravitational variability and from. Okay. You may not have a clear reason why we ignore alpha t, but again, we have to postpone it to the part. I usually prefer to introduce first the CMB and then inflation, because we have to keep in mind what are the data. We have to, I like an empirical approach, and I prefer to use the theory later to ease all the tensions you may feel when you see incompleteness in the description. Anyway, another interesting observable is the so-called tensor to scalar ratio, which is the ratio between the tensor spectrum and the scalar spectrum. So you can parameterize the scalar spectrum with these two quantities. You could add more, but in general you don't need to do that because they are negligible and they are generally small. And you do the same for the power spectrum of tensor perturbations, where K0 is called pivot scale, and it's the typical scale of your experiment. For WMAP and Planck, the typical pivot scales are 0.05 megaparsec to -1, or in alternative 0.00 megaparsec. It's, there are numbers which depend on the characteristics of the spectrum. And these are some numbers not updated. This is from 2015, but the actual numbers are quite similar. What do we observe? We observe a scalar spectrum which is very close to the Harrison-Sadovich spectrum, but significantly deviating from it. It's a 0.9697 plus or minus some error bar, which is small enough to state that. So I'm stating statistical things correctly. But it is significantly different from Harrison's spectrum. This was a great achievement, confirmed first by W. Marco, because it created a challenge to explain why we are so close to Harrison's spectrum, but quite probably away from it. Okay, so this is another question mark. Put here back. Why are we closer to Harrison's spectrum, but without reaching the perfect scaling variance? Now, the other observation, which has a heavy implication for quantum gravity and modified gravity models of early universe, is that the tensor to scalar ratio is smaller than, actually it's 0.06 nowadays. So the tensor spectrum is much smaller than the scalar spectrum. The amplitude of the tensor spectrum is much smaller than the scalar spectrum. It's something that we kind of anticipated here, and this is variation. Why is that so? Another question mark. But this observational bounds are important. This is actually at 1 sigma, and this is at 2 sigma. 95% confidence level. My friends. These are figures which are taken from the NASA WMAP website, are rough illustrations of what happens if you fix all the parameters of your model and you vary on one. So in this case, it should be lambda Siriana with the lambda given by the best fit, but then you change the k to +1 or -1. This is -1. So there is a topological.
Because here parts are yes, I mean, we know that for the parameter, the parameters, the best is around 1, but it is
yes, but when you have a fine tuning, we will have to explain. But that's the so-called Platinum problem. But I don't remember really the origin of this. I'm not even sure whether this probably this comes from an actual simulation. But in general, if you trigger a curvature and you give it its contribution high enough weight over the total, then you will start to see unacceptable. The thing is that if you have a having curvature would mean that your light rays from cold spots are bent, and vector for the observer would mean to see effectively bigger or smaller features, depending on this is the typical. This could be a question for a tutorial. Basically, if you have a feature which size is observer for a flex universe, you will have you will measure it with you will say that this has a certain always at a certain angle. But if the universe were closed, then the light rays would be convex, but you would effectively see something with powers in the and vice versa. So you can make this constraint of curvature by looking at the map data and see whether the pattern of spots is more compatible with one another. And in an experimental error, the result is that the universe is probably flat. So you can magnify this. You can magnify this to the point where you start to see the deviation of these plots. Maybe I will show you the slide tutorial. More questions? No, then let's move on. In the last 20 minutes, let's talk about first part of inflation. So the Big Bang problem, the Big Bang model has several problems we didn't talk about. What is the flatness problem? Why is the universe so close to flatness? This problem can be rephrased as an initial condition problem, which basically states that to have the density contribution of a curvature evolves through time like all the other densities. Nowadays, we can state that the universe is flat. But if we go backwards in time, then we would expect, so basically flat means that the contribution of the curvature is strongly suppressed. If we go backwards in time, then we would expect this contribution to increase. But if we want to get the value today acceptable, compatible with data, we would have to impose a specific initial conditions for this component, which is strongly fine-tuned. So why should we fine-tune this component so that to get a very flat universe in as you observe it, the public web model doesn't explain it. And we have a horizon problem. You see, the CMB map is the map of the whole sky, and we see that up to these 10 to the minus 5 fluctuations, it's isotropic. But hold on a second. How big was the universe when the CMB was formed? In terms of angular separation, we are talking about 1.3 degrees. It means that the causal horizon of the universe, when the CMB formed, was about 1.3 degrees. So this means that the causal patch here and the causal patch there were disconnected at the time. Okay. Still, they have the same temperature. How is it possible? But is it violating causality? Is there some process which no local stating that I mean, imposing that the temperature at the causally disconnected parts of the universe should be the same? This is a problem that the back model doesn't solve. Then we have another problem which we have already seen, which is what is the origin of these anisotropies? We observe that, that's fine, but we have an explanation. This is related actually to the other question of why do we see something which is compatible with almost a scaling variant power spectrum. The solution of these problems is inflation. It is nowadays a part of the standard cosmological principle. Let's start with the kinematics, meaning that we describe inflation as in terms of cosmological parameters without giving a dynamical explanation. By definition, inflation is any phase of accelerated expansion. So whenever the second time derivative of scale factor is positive, then we can talk about inflation. The universe inflates. And actually, if you look at the second Friedman equation, if you remember it, or if you have it in your notes, you will see that this is possible only if the first slope parameter epsilon is smaller than 1. This is a kinematic definition of inflation without any reference to the origin of this acceleration. However, we have a first hint by noticing that the second Friedman equation on the right-hand side had minus a double dot proportional to minus rho plus 3b. So that thing is positive when the barotropic index of the perfect fluid is smaller than minus 1/3. Prototypical inflation background is the sitter. The sitter is defined by a constant Hubble parameter. And when h is constant, then the scale factor is follows an exponential flow. And in this case, the first slope parameter is 0 at all times. So obviously this background is an accelerated background. But you don't have to go to the sitter to have other also power law background can give rise to acceleration. How does it solve this? So let's assume that the universe was accelerating. We still don't know how, but let's assume that it was accelerating at 3 times. And let's see if this solves the flatness and the horizon problems. Okay, so this is the density in terms of this is the energy density divided by the critical density of a curvature term, which is given by K, which is order 1, so it's plus or minus 1, or it's 0. But let's assume that it's not 0. So we have a universe with no 0 curvature times the co-moving Hubble radius, which I remind you is this. For an accelerating universe, the co-moving Hubble radius is a good approximation of a co-moving particle radius. So the co-moving Hubble radius tells you what is the co-moving size of a causal function. Now, you can discover by back of the envelope calculation that the time derivative of the co-moving Hubble radius is proportional to epsilon minus 1. So, if you have a normal matter components where the barotropic index is bigger than minus 1/3, you will have a positive epsilon, sorry, an epsilon greater than 1, and then this R dot will be positive. It means that in a standard situation like during radiation domination or matter domination, the co-moving Hubble radius grows in time, which means that also the curvature component grows in time. So this was the flatness problem. If it grew in time, if it grows in time, and we don't have acceleration, and we already know that nowadays this omega k is negligible. It was even more negligible at 30 times if it always grows. Okay. But if we have a phase of acceleration, then the problem is solved. Why? Because we can start with an arbitrarily large curvature component, and during inflation, it decreases because here epsilon is more than 1, so R dot is negative. So it decreases, and if inflation lasts long enough, then you can reach very, very small values, which take a long time to start growing again. So today, we will still observe a very, very small curvature component. Okay? Provided the inflation lasts is long enough. Okay? Is it clear how it solves? This is a kinematic explanation of the flatness problem. If we had inflation from some initial to some final time, then no matter how big this was, but if it's long enough, it will be suppressed, strongly suppressed, exponentially suppressed. But today we would still observe a very small curvature. The horizon problem is solved. The plot is so this thin line is the wavelength, the proper wavelength of some perturbation, and the thick line is the Hubble rate, capital R, which is rate. So it's A times RH. And if you prefer co-moving distances, you can follow actually the bottom plot, which is co-moving wavelength, which is constant, and co-moving Hubble radius. So before inflation, the Hubble radius was growing, and so was the wavelength of the perturbation, because it's proportional to the scale factor. And the scale factor grows in an expanding universe. But then during inflation, the Hubble parameter becomes approximately constant. So here the growth stops more or less, but lengths are exponentially stretched, are inflated, to the point where this perturbation, which was well inside the horizon, at some point grows and passes the horizon size. Then inflation ends, and the Hubble radius again starts to grow. Also, the perturbation, also the wavelength grows, but not as fast as the Hubble radius, until the Hubble radius catches up and includes again this perturbation. So, for such an observer, at late times, it's like we entered into contact with this perturbation when it entered the horizon for the first time. But in fact, with an inflationary phase before, we discovered that this perturbation was already inside the causal pouch. So this means that all scattering processes of the particles of the plasma, the hot plasma at the beginning had well, at first actually there were no particles, there was only main photon we received. Anyway, whatever was generated during inflation had the time to get into well, what was following the causal physics. Then these perturbations were inflated outside the horizon, so this is a beautiful sight. And then they reappeared again when the inflation ended and the horizon started to move. So the moving picture is something like this. So during inflation, the moving radius decreases, so it shrinks beyond the moving wavelength, and then again it grows and it improves inside. So basically, the patches that we see at larger separation were in causal contact at the time when we were well before the CMB, because inflation took place before the CMB, but there were patches in causal contact at some point in the past. So we are not violating any causality principle here, and it's just a result of the fact that the universe was accelerating at very early times. And then the other problem of the primordial seeds, I will let up that. Let's see now a bit of dynamics. What drives inflation? The simplest candidate is a scalar field. If you have a scalar field slowly rolling along the potential, then you get acceleration. Why? So this is the barotropic index for the scalar field. Here I just divide the pressure, which is kinetic term minus potential, by energy density, kinetic term plus potential. But if the kinetic term is smaller compared to the potential, then the barotropic index is close to -1, which is the equation of state for cosmological. So if you have a scalar field with a potential such that you have a phase of slow roll, then you have acceleration. You may ask, the universe is also accelerating today. So do we have another scalar field? That was an attempt to solve the cosmological question problem, but it doesn't work. Anyway, so the picture is that the universe at the beginning is cold, and it's filled only with, it's empty, but filled only with the inflaton field in its vacuum state. Then it undergoes a phase of inflation, and at some point inflation ends because of maybe if you have a potential to the plateau, then you may reach some minimum. So the field starts to roll quickly in the potential well, so inflation ends, and the classical oscillations in the potential well actually translate to cosmological fiction we have. But they translate at the quantum level to the decay to particles. And this happens at some temperature. This then creates this hot plasma of particles, and eventually from this you eventually get the standard matter atoms, etc., as we saw in the optical Big Bang model. Anyway, the universe reheats suddenly or not, depending on the model, at a temperature which observations are set to be no greater than about 10 to the 16 G. So it's the grand unification scale. And then you can estimate the duration of inflation in terms of the number of e-foldings. You can measure it in two ways. Either you measure the total duration of inflation from beginning to end, or from the point the perturbation leaves the horizon until the end of the inflation. In general, it's better to use this second definition of number of e-folds, which is the logarithm of the moving our horizon at the horizon crossing. Horizon crossing is the moment where the perturbation leaves the horizon, and the Hubble radius at the end of the inflation. Its duration depends on the heating temperature, on other parameters, but it's the first term is about 52, and this is about the typical duration of the minimal duration of inflation, about 50 folds. It roughly means that the universe had to exponentially grow like 8 times from the beginning to end of inflation as a minimum to solve the flatness problem. After one can re-express, I don't show it here, but one can re-express this, well, it's easy. You can express this Hubble radius in terms of e to the n, so exponential of a number of e-folds. So the more e-folds, the longer the duration of inflation and the flatter the universe. And you have a minimum requirement to respect the observations. So this is an extension of the previous timeline of the universe, but considering a very early phase. So this is a condensed version of the previous table. So today at 10 to the 17 seconds from the beginning, at radiation equality happened when the universe was 100 times smaller. By universe, I mean here our causal patch, not the size, physical size of the universe, which would be infinite. At the BBN, it was 10 to 8 times smaller, about 200 seconds. These are famous first 3 minutes of the book. And the latest time at which inflation could have ended was 10 to the minus 2 seconds to respect the BBN constraints. Here there are question marks because it depends on the model. But again, we can talk about possibly a universe which starts with a 0 temperature and very high energy. We have question marks about the scale of inflation, but that depends on your particle physics model. But this part of the called the Big Bang is essential to make sense of what we are observing. So nowadays, when we talk about the lambda linear model, we also include inflation because that's part of a deal. If we want to train observations, we must. There are no known credible alternatives to inflation, because it explains too many data. If you have a new model which explains some data, it's good, but it should explain at least as many data as the standard cosmological model. And finally, let me conclude because we run out of time. It's useful to introduce the towers or parameters, which are parameters which can be defined by the features of a potential and its field derivatives, or from the Hubble parameter. There are two different towers, and these slope parameters are smaller during inflation, and they're almost constant because of their their time derivative is the second order in the parameters themselves. That's why it's called a tower, because you have a leading order parameters which are smaller, and then you can introduce higher order parameters which are progressively smaller. You can do it in different ways. You can relate them by simple relations. For instance, if you have a potential coming from your model, you can use the tower, this tower parameters. Or if you know something about the kinematic of the universe, you know the scale factor, then you can start with this other tower, but they are related to each other. So the first parameter is the same, and the second parameter eta is related to the eta of the other tower by this relation. And you can compute things. You can compute the number of defaults. Once you know how your potential, you can compute the reference parameter, you can integrate it, and you get the number of defaults. An example is a monomial potential, so this is just a pure power law with n equal to 2, 3, 4, whatever. You can compute the slope parameters. Here I leave it only to the first two. You can compute, the value of a field at the beginning and at the end of inflation, and when you integrate, you can get the number of defaults. So one thing you can do is, if you fix the number of defaults to some value, typical value, or to the minimum value, then you have a prediction for the slope parameters, and these slope parameters will enter the power spectra as a BBC2 model, because I run out of time. The second model is a national inflation, which is maybe motivated by a symmetry breaker mechanism, which is the cosine, the potential is periodic. And again, you can define, you can calculate the slope parameters. You find in this case that eta is much bigger than epsilon, so this will give a main contribution. And again, you can calculate the value of the field, which is not an observable, because the value of the field is not observable, but it enters it's not observable. And the beginning at the end of the function. And this is actually the value of the horizon crossing for a calculation of the program number. Tomorrow we will continue with the solution of a cosmic six problem, and then also see how these slope parameters are cosmological observable. Okay, I'm done for today. If you have many questions, comments, skeptical remarks, too shocked, too triggered? Yeah.
I actually read I don't think we're going to say in the last 5 months. That's why I see how in the first part of the lecture, I cannot judge each of the standard rules. So I know there is a function historically. I wanted to know if there are ways to determine.
Yeah. You calculate it from a number of, depending on the number of relativistic and non-relativistic particles, you have a species of particles. And with the standard model, you can calculate it. Depending on the energy of the temperature of the universe, some particles will become non-relativistic at some point, some number point. And it's a number that you compute is order 10. It's not 10, it's it's a perfectly calculable number.
species of the particles not determined.
No. Yeah. So I didn't understand that for your question. Can you repeat it?
Which units are more like
No viable.
no more like
More viable.
yeah, like the defined model of dark energy and scalar field, like using the same sample of dark energy and condensation, or models coming from bouncing cosmology and of reducing the same level of computation without adding information.
I would say that none of the models which work has given a viable solution to the cosmological constant problem. By viable, I mean something where everybody agrees that the is one. If you want, it's a cultural concept of viability. Because you can have a model without fine tuning, then there will be other problems like assumption or assumptions, or it doesn't explain. Maybe it explains only vector, but then it doesn't explain anything about the other observations. There are models which unify dark energy with work. There are many that which don't work, because there are some that work. But again, there it's one could question whether there are very fine tuning initial conditions, or if their scope is too limited, or if they are not embedded in a fundamental theory. In general, we are talking about models, not theory. I don't think there is a strong enough candidate making happy the majority of the community about the solution of this cosmological conceptuality. Much harder than the different problem. So you can fish in the literature models, define models on fusion dark energy, and I can also give you references. But we could have a general trouble of these models and see what their shortcomings.
Like all the ones that say that they don't need a parallel translation.
They don't need what?
They don't need a parallel translation. Like there
are there are alternatives to fiction. Syngas cosmology, for instance, is you may see it on Thursday, because the method creates actually a stochastic background, stochastic additional background of high amplitude. That's an alternative translation. You don't have a scalar rolling, you have a gas springs in thermal equilibrium, which undergoes some funny stuff. But again, yeah, it's in the realm of the possible. But it could become, models like that could become important if they gave a new prediction, like this one, like suppose we observe a stochastic background with the cycle. The cycle is not even an approved experiment, so maybe we won't have it. Suppose we have it, and suppose it observes a stochastic background, and suppose we are able to discriminate between other models with that level of stochastic background. Then I want to say, oh, this model is now is becoming more interesting than the standard. Or some level of node of shanity that we haven't detected yet, or some polarization we haven't detected yet. That's what people are working on multiple predictions, because explaining only one thing doesn't make a model strong enough to compete with CDM, which is simple. It has problems, but it works within our knowledge.
So if I prepare my general model of inflation, how should I test it? Like, do I measure the scalar to tensor ratio or?
Yeah, you could calculate the spectra. I suppose that you would have potential, so you would calculate the slope parameters. From that, you would calculate the spectra with spectral indices, spectral value, which may be useful also for the stochastic background, the tensor to scalar ratio. It would have to explain it meant to be compatible with data, like natural inflation, for instance, or arbitrary inflation. And suppose it's compatible with data, then you would have to start to look at something new, like high amplitude stochastic gravitational background, or high non-Gaussianity, but not too high, because we have bounds on non-Gaussianity. Polarization, which we haven't observed with the polarization, for instance. What about the discrepancy about the value of the Hubble parameter, which is people are debating a lot nowadays.
So I mean, like, what are the observables that are existing right now?
Oh, well, CMB observables, barrier acoustic oscillation from large scale structure. For the stochastic background, what do you have? Gravitational lensing. You have the bounce from LIGO Blockaga. We are writing a long paper about all possible things about the test, neutrino physics, astrophysics, matter. What about dark matter? I haven't said anything about dark matter. Okay. Is it made by particles or by modification of gravity? So you have gravitational lensing, rotation curves. It depends if your model is a model of an early universe, then your scope is limited to larger scale observation like CMB. It depends if it has some case or extension or certain later evolution of the universe. It depends on many things. So that's what we want to do. In my opinion, it depends on where it comes from. So if you can always find an ad hoc model fitting everything. Now the real challenge is to find such a model from a fundamental theory. This is what I'm working on. So I try to find predictions from a fundamental theory. It's not. That's what Renato was saying yesterday in my talk. But I would start as a step 0 to check that it is compatible with CMB observations. If you have a new model of inflation, you can do that with a likelihood analysis. And I will show on Thursday plot on R versus NS, where your model should lie. Don't worry if you come up with new questions, you can send me an email and I will comment them for the tutorial. So thank you for your patience. You are your ignorance.
So we are going to close the session now because you will be sad to learn that Professor Torigo couldn't come for the tutorial session. So this tutorial session about statistics is suspended. We don't know if there will be opportunity to do it on Thursday, but it's not sure. So we will close the session now. Thank you very much.
How many?